Joining us today is Joe Callingham. He'll be talking about special relativity. So I think we better get started, Joe.
Yep,
Thanks.
Sounds great. Thank you, Jenny. Welcome guys to CAASTRO in the Classroom. My name's Joe Callingham. I'm from the University of Sydney, where I'm a PhD student here. But I did my HSC syllabus back in 2008. It's been a while, but the syllabus hasn't changed. And so today, what I'll be talking about is in fact the bizarre world of special relativity and how that fits into the HSC syllabus, okay? So guys, I love questions, and I think that's probably one of the best ways to learn is by asking as many questions as possible. Now this system we have developed, this videocon system, doesn't overly make it very easy to ask questions, but feel free to interrupt anytime you like. But I find some people are uncomfortable in doing that, so just jot down your question on the bit of paper and the slide and ask at the end if you feel uncomfortable interrupting me halfway through my talk. But again, I'm happy to have questions at any time. So welcome to the bizarre world of special relativity. So why is it so bizarre? I'll come to explain, and really why is it so it's such a weird way of thinking. It's all got to do with some of the Einstein's thought experiments and some of the things he unveiled. And so let's get underway and we'll begin from there. Okay guys, so just briefly, I sometimes drop into this term called SR. All that means is special relativity. It's just a short way of saying it. So if I ever use that, just make sure you're on the same page. Whenever I say SR, I just mean special relativity. Now, just like any good talk dealing with the physics of special relativity, I think you should start with a very famous scientist and one of the best educators in physics, and that was Richard P. Feynman, who won the Nobel Prize in physics. And what he has to say about special relativity is actually quite interesting. He states that you'll have to brace yourselves for this, not because it's difficult to understand, but because it is absolutely ridiculous. And so that's what special relativity is. Your intuition is completely destroyed when you start to travel near the speed of light. Things are very different now, and what you expect to happen actually don't happen at all. And so that's what we'll be talking about today, and I'm going to give you some hints and tricks that through the HSC you'll hopefully be able to utilize to your advantage, and actually when things such as your intuition fail, you can always fall back on these kind of tricks I teach you through this talk, okay? So really the warning I want to say here is that special relativity is bizarre. And if you're confused, you're kind of on the right track. You just got to try and keep your bearings, and hopefully some of the things I'll teach you today will really help with that. So as I mentioned before, this talk is all based around the HSC syllabus, and these lovely dot points you probably all know and love by now. Just to help you guys identify what part of the syllabus I'm talking about, what I did was just number the idea that's dealing mostly with special relativity, 1 to 10 on the left column, and then 11 downwards on the right column. And so when I go through my talk, you'll see these red numbers at the top right-hand corner of my slides. And so for example, on the next slide, you'll see 2/3. That means I'm dealing with the dot point 2, dot point 3 here when answering the HSC syllabus, okay? Just so you can keep tabs with that. So to start the talk, we begin with why do we need special relativity? Now the HSC syllabus focuses in particular on the Michelson-Morley experiment. Now it's somewhat a simplistic assumption. Science is takes very convoluted paths through to discoveries. Okay, it's like wandering through a forest with many different branches, and you eventually all converge on one. One of those paths is the Michelson-Morley experiment. Now the HSC syllabus has emphasized it, so I'll talk about it briefly here in this talk. But it starts to set up the realm of why do we need special relativity. Okay. So what was the Michelson-Morley experiment all about? So I want you guys to imagine you're a 19th century physicist. You're sitting down and you're considering waves. You think of water waves. You think of sound waves. And when you think of all those things, the thing that always unites them is the fact they all travel through a medium. So for example, water waves have water as the medium, sound waves. So when I talk, that is the air of the medium. All waves are essentially travel through a medium, as far as you're aware in the 19th century. So when experiments start coming out, such as the young double slit experiment, stuff like that, just showing that light itself is a wave, people began to consider, well, obviously there must be a medium there. Okay, and so it's obviously not air, because light can travel through space where there is no air, and so there had to be something else that they postulated, something they called the ether. Okay, now you might see it spelt with an A, without an A, it's all less the same thing, it's just Latin, being the usual difficult thing it is itself, much harder than physics. What you've got here is just essentially a way of testing whether this ether exists. That's all the Michelson-Morley experiment tries to do. Now what I've got is a brief diagram on the left, and this is showing you how essentially you get an interference pattern by the way the ether is meant to be traveling, okay? So what you've done is got an interferometer, and you get a pattern where that guy's head is with the telescope. Now, this pattern should change depending on the motion of Earth through the ether. So what they did was they measured this interference pattern as Earth is at one point of its orbit, and then measure the interference pattern on the other side of the orbit, and if the ether existed, you would expect to get a different interference pattern. And what in fact Michelson-Morley discovered was that interference pattern, just imagine it's just stripes, more or less, didn't change. It stayed the same, okay? And so this led to what's famously called as a null result. It didn't prove or disprove the ether existed, just said, well, it's not evidently there, okay? And so this kind of left the door open for special relativity to come through, and what we'll come to show is that special relativity explains this result via its postulates. But yeah, this is the way the HSC syllabus introduces the idea of why we need special relativity, because, hang on, light doesn't quite need a medium to travel through. Okay, and this has all got to do with inertial frames of reference, as we'll come to talk about. But I find that very difficult to think about. What you're talking about is ether, what you're talking about is interference patterns, you have to worry about the properties of light. What I want to do is talk about something a little bit easier. What I want you to imagine is there is a thing called a muon. Now, what this is just a meson, it's a particle, it's like a proton or an electron, but it's unstable, okay? And essentially what happens is, these muons in real life are born at the top of our atmosphere, and they're unstable, so that means they actually decay and disappear. Now, they travel at close to the speed of light as well when they're born. Now, obviously it's not important as a muon. Just imagine it's a ball. So I've got a ball in my hand, just imagine a ball is born at the top of the atmosphere, and after a certain amount of time, that ball completely disappears. And that ball's travelling close to the speed of light. Now what we find is that if we just use Newtonian mechanics to explain the lifetime of this ball, how long and how far it travelled, we get very different results than what we'd expect if we actually use special relativity. And so this can lead to some very different and wrong predictions. In particular, the decay time, how long something lives. So for example, if I just observed how long I expect that particle to live for, I'm going to get different things depending whether I use Newtonian mechanics or Einstein mechanics. What we'll actually find is that the amount of time that particle lives or that ball lives is actually dependent entirely on the frame of reference it's in. And that idea is really profound. Essentially means that things will appear to live longer in different frames of references. But we'll come to deal with that more as we go through, because what we have to do is introduce the star of the show. Now, a lot of mechanics and all of special relativity deals with what we call reference frames. Now, what's a reference frame? Well, you use this every single day. When you're traveling in a car, you're traveling on your bike, you're walking. Alright? So imagine you're in this full drive I have in the bottom corner, and I'll give you a call. And you could say, oh, I'm traveling at 100 kilometers an hour. Now, that's not enough information. That's not defining your reference frame, because reference frames are always defined relative to something else. For any mathematicians that are particularly inclined, all you're doing is setting up a coordinate system. Okay, guys? But a reference frame, you have to describe relative to things. For example, if we're in this car and we're traveling 100 kilometers an hour, we have to ask relative to what or whom. So, for example, if we go past a billboard that's stationary, right, on the side of the road, we're traveling 100 kilometers an hour relative to that billboard. Now, if we had a partner next to us, a passenger, a friend, okay, and he is in the same car as us, obviously he's not moving relative to us, and so therefore relative to his frame of reference, we're doing 0 kilometers an hour. We're both traveling at the same speed. Okay, and then we can also imagine this car, this van on the left here, this red van coming towards us. Okay. And what you have there is that, imagine it's doing 100 kilometers an hour, we're doing 100 kilometers an hour, so relative to incoming traffic, it'll appear we're traveling at 200 kilometers an hour. Okay, because you have to add in the addition of the other person's velocity. So a reference frame is, you always need to specify relative to what. Okay, and this is where a lot of the difficulties of special relativity come into, because you need to ask, who are you relative to? Now, before I come to explain a bit more of the tricks, hints and tricks, they're always trying to get that answer right, I need to talk about what's so special about special relativity. Now, we've used the word special relativity. What's so special? It deals with a particular reference frame, and that reference frame is called an inertial frame of reference, okay? What does inertial mean? It means constant speed. 0 or constant speed relative to another frame of reference, okay? So, that means no acceleration. You can't be in the rocket and use the special relativity to calculate, say, how long something will live. Okay? Same thing, imagine in my car, if I'm traveling 100 kilometers an hour and I don't have my foot on the accelerator or the brake, I can use special relativity to describe my motion. But as soon as I put my foot on the accelerator, or as soon as I put my foot on the brake, I undergo acceleration, and therefore we're no longer dealing with special relativity. What you actually need to go there is actually Einstein's other profound theory called the general theory of relativity. But HSC only deals with special relativity. And it makes the maths a lot more simple, trust me. Alright, so let's just talk about quickly, now we've introduced frames of reference, and we note that they are, the way to talk about this is always considering relative to what or whom. Let's talk about Einstein's postulates. These are the fundamental tenets. These act as a skeleton of which special relativity is built on. Now the first one is the principle of relativity. Now, this traces its realm back to Galileo. I remember learning this in the HSC and thinking, why is this such a big deal? You know, it's essentially, the principle of relativity is stating the laws of physics are the same in every inertial frames of reference. That seems pretty obvious to me, it doesn't seem like a big deal, but it actually is quite profound, and it's a little bit more philosophical than physical, but you need to state this, otherwise it essentially means you can't compare experiments. What it means is, if I had this ball, right, and I drop it, and then I conduct that same experiment on a train, and I'm going to measure the speed of gravity in both those frames, I can come back, we can come back to a central point and discuss our results and compare our measurements. Without the principle of relativity, we can never do that. And therefore, you can never make comparisons and the whole theory just falls apart. It seems somewhat, it's not as though it's important, but it's actually very important to be able to do that comparisons. Otherwise, you'd never be able to get the differences. Okay? But really, at the end of the day, the principle of relativity doesn't form a very important aspect of the focus of the HSC. The next one is where the fun comes in. The second postulate is the speed of light is the same in all frames of reference, independent of the motion of the source. Okay, so we know the speed of light, often expressed by the letter c, is about 3 times 10 to the 8 meters per second. But what's so special about this postulate is stating that the light is independent of the source. Now this is kind of weird because this leads to the fact that one, events aren't simultaneous anymore in one frame of reference relative to another, and two, length, time, momentum are now all relative. There's no absolute that was in Newtonian mechanics. So let's try and get these postulates into a physical example so we can feel a bit more, we can get a bit more of a better grip on them. So I want you to consider 2 inertial frames of reference. One, I'm just going to call a big S, which is just the observer at rest on Earth, so us. Just imagine we're on Earth and we've got telescopes and we're looking at a spaceship that's moving at a constant speed, okay? And what I'm going to describe that is actually as S dash. That's the frame of reference. Now, imagine the situation, any Star Trek fans, essentially they're shooting photon torpedoes now, or a missile. So we've got a spaceship that's traveling 1,000 kilometers a second relative to us on Earth, and then they shoot a missile that's traveling at 2,000 meters per second. Now, relative to us, what we do to work out how fast that missile is moving relative to us, all we do is add together the speed of the spaceship, the speed of the missile, and that's how fast it has to be moving, okay? So it's just 2,000 plus 1,000, we would measure that missile is traveling at 3,000 meters per second. And that's what Newtonian mechanics tells us. And it's very simple. Now, what Newtonian mechanics would say, instead of shooting the photon torpedoes, we actually shoot lasers, right? Instead of shooting an actual physical missile, we actually shoot a laser beam, or a light beam. And now this is very different because what Newtonian mechanics would tell us is that to work out the speed of light, right, all we have to do is add together what speed it is, plus the speed of the spaceship, which is 1,000 meters per second, and that's the speed we'd measure the light to be traveling at relative to us. But that violates Einstein's second postulate, which states that the speed of light is the same independent of the motion of the source. In fact, if we conduct this experiment, what we'd measure is the speed of light is in fact c, independent of whether that spaceship was traveling at 1,000 or 2,000 or 5,000 meters per second. So, how do we fix this? How can we fix up this system and actually justify, hang on, if speed of light now is independent of the source, what does that mean for space and time? So, special relativity is not complete unless you start talking about trains. It seems like every thought experiment involves trains, but they're very simple and easy to conceive of. thought experiment I want you to imagine is that we're in a train carriage. We're standing directly in the middle and there's a light bulb dangling above our head. And it's perfectly situated in the train that it's equal distance to the front of the train and to the end of the train. Okay? So that means as soon as I pull and turn on that light bulb, the light hits the front of the train exactly the same as the back of the train. Simultaneous is the word. Alright? It hits the front and the back exact same time because it has the same amount of distance to travel. Okay? The distance to the front and the distance to the back is the same. Because I'm in that frame, it looks like it's stationary. Now, what I want you to imagine is we step back and we are on a platform as this train goes by. And we have a little remote that turns on the light. And we have a telescope and we're staring through the window of the train and we hit this switch to turn on the light bulb. And we measure how long it takes for the light to hit the front and the back of the train. And what we actually find is that the light is in fact going to hit the back of the train before it's hit the front of the train. This is because the speed of light is now independent of the motion of the object. What's happened is the front of the train has moved slightly ahead and the back of the train is catching up, so when I turn on that light, the light actually has less to travel to the back of the train than it does on the front. So what you'll see is it hit the back first and then the front. This is pretty strange, guys, because this means that something that was simultaneous in one frame of reference is no longer simultaneous in another. Okay, so that means space and time have become relative. And as I stated, things that are simultaneous in one are not simultaneous in another. So this really becomes now to the bit more of the mechanics that the HSC focuses on, and this comes to what's called time dilation and length contraction, and mass dilation as well. So let's begin with time dilation. So this is an equation hopefully you've seen before. I'll describe it anyway. This is sometimes described as a Lorentz transformation if you want the technical term, but more or less this just shows you how to transform the time of one frame of reference to the time of another. Now, what you've got is, on the denominator, you've got 1 minus the square root of 1 minus v squared on c squared. Now, v is just the speed of the object we're interested in. C is obviously the speed of light. Now, the difficulty of the HSC syllabus, and where most people go wrong, is identifying which one of these is T0 and which one of these is TV. Now, T0 usually is the time of the event in the frame that is stationary, and TV is the time of the event that's in the moving frame of reference. And let's describe an example of that to make it a little bit more clearer. Because the trick comes here is that both frames of reference actually see each other moving relative to each other, and that's where special relativity gets hard. So you should always ask you, what frame of reference are you in when you want to answer that question, okay? Which one's T0 and which one's TV? So, again, we have another train, and we've got two people. We have Alice that's sitting on the train, and Bob that's standing out. Again, special relativity can't be complete without an Alice and a Bob. So, imagine we've got an observer. Imagine we're on the train sitting next to Alice. And for some reason, Alice manages to spill coffee on her lap. And let's just say that takes 2 seconds. So an observer at rest will measure, that will be our T0 essentially in this situation. Now what I want you to imagine is that we're now Bob standing outside and he observes this event. He observes Alice spilling this coffee on her lap. Now, since the train is moving at a constant velocity v, it's now in the frame SV relative to Bob. Notice I'm saying relative a lot here, relative to Bob. And so what he will measure now is a different time, and that time is TV. And that's a different time that takes to elapse. Now the question is, let's actually put some numbers here. The hand and the trick here is always to remember that moving clocks run slow. You should always get an answer if a clock is moving relative to someone else's. So, for example, Alice's clock relative to Bob's clock, her clock will always move slower than Bob's clock when it's asked relative to him, okay? So the trick here is, remember, moving clocks run slow. So that means, now I'll go through a bit more of an example next, that imagine the train's travelling at 0.01 c, so about 10% the speed of light. What happens is, if you just put the numbers in that calculation at the top, you'll find that TV is just slightly longer than T0. And obviously, as you get closer and closer to the speed of light, you go much faster. And, the time goes much slower. You can find that essentially you've got an extra 15 seconds, 15% gained on that. So let's think of something easier again, and this comes back to this muon experiment. So remember my ball that's born at the top of the atmosphere. Imagine 3 kilometers up in the atmosphere, and we measure it traveling at 98% the speed of light, or 0.98 c. You often see it written. We can do a couple of cool experiments and calculations. So what we're going to do first is imagine we're in the lab frame. So we're the people on the Earth looking up, and we see this ball born, or this muon born at the top of the atmosphere. What we want to know is, we know from our own experiments with muons or the balls on the ground that they live pretty much for about 2.6 microseconds before they disappear. So 2.6 times 10 to the minus 6 seconds. So they live for about that period of time before they disappear and die. So that's what it is at rest. Our work at muons at rest, so essentially at the same frame of reference to us. So we've got all our calculations here. We know that what T0 is, how long it lives for, okay? And we also, when it's at rest relative to us. But now it's no longer at rest relative to us because it's traveling at 0.98 c. So we want to know how long it will live now, given this situation. So all we have to do is plug in the equation. So we've got our time dilation equation. We know what T0 is because it's the amount of the lifetime of the muon when it's relative to us, when it's not moving relative to us. And so you just put this in. Now there's a little trick here that can save you a bit of time during the HSC. A lot of people would go then and just do the velocity is equal to 0.98 times 10 times by 3 times 10 to the 8, and then square it and do all this kind of stuff. If they give you it as 0.98 c, you can actually see on the denominator here, under the square root, you can actually cancel the c squareds out without ever having to put it in your equation. That's useful. It stops silly errors that you might put in your calculator, and 2, it just makes it a little bit quicker. You can see more or less what's happened is the c squareds cancelled. I never needed to know the exact speed of light in this situation. And then what you do is just divide by the square root, and your answer comes out to be 13 microseconds. Now that's crazy, guys. Just think about this. This object, when it's at rest relative to us, lives for 2.6 microseconds. But when it's moving at close to the speed of light, we observe it to live for nearly 4 times longer. Wow, that object relative to us seems to have 4 times longer life when it's traveling at 0.98 c than it does when it's not traveling at all. This is why special relativity is so strange. That's just completely bonkers to think something could live differently. So let's imagine how far it travels as well. We can ask that question too. So since we observed it to decay in about 13 microseconds, we can ask how far does it travel before it decays. And now this is just simple v equals d on t. So L naught, that's how far it travels, equals the velocity times time. Once you put all those numbers in, what you find, and this time you actually do need to put in the speed of light 3 times 10 to the 8 meters per second, what you find is that it travels about 3.8 kilometers before it disintegrates, before it dissolves, before it dies. So that's what you'd measure. So when you see it born at the top of the atmosphere, it will live for about 13 microseconds and it'll travel 3.8 kilometers. Now we can ask all these exact same questions in the frame of reference of the muon. So I want you to imagine you're riding this muon coming to the ground, and this is where the trick comes and to think about. Now the muon is stationary relative to you. What's moving is the ground. The ground's rushing up towards you. This is the same thing for a skydiver. It looks like to a skydiver, if you had no acceleration, you're just traveling at perfect speed, that the ground is rushing up towards you, okay? And that ground is rushing at 0.8 and 0.98, 98% the speed of light, or 0.98 c. Since we know the lifetime of the muon, we can easily calculate the distance it should travel, because it's at rest, right? So it's only going to live 2.6 microseconds. That's what we figured out when it was at rest in the lab. And so again, you just use v equals d on t, and before you know it, you've just got an answer out of 0.64 kilometers. Now, but didn't we just calculate the distance it traveled to be 3.8 kilometers? How do we interpret these two distances? Again, this all comes to the fact that distance is now relative. It's no absolute. And so in fact, you can see yourself traveling at these two, you can justify the fact that you're going to observe two distances traveled. So going back to the muon frame, Imagine it's appeared at the top of a mountain. Okay, this ball has appeared at the top of the mountain, and we want to say, imagine how big it would measure that mountain to have. How big is that length? And we actually know, this is the other equation you'll become familiar with if you're not already, is that the length of that mountain will be contracted to be consistent with what we just calculated before. So this is similar to the equation as before, just what you've got now is T's and TV and T naught replaced by LV and L naught. The naughts and the V's mean the same thing, but the key difference here now is no longer a division, it's actually a multiplication, okay? So that means lengths are contracted, right? Rather than, and time, while time is dilated and broadened. So just putting in those calculations, what you find is LV equals 3.8. You put all those things in because you know your L naught, that's the length of the mountain as though you measured it when it's completely stationary, when you're stationary around the mountain, and you get the exact same answer back as before. So they're completely consistent. This is what you found when you were in the Muon's frame, and how long it will live, and how long it seems to travel, and so what you'll find is they're consistent. And this comes to our second tip, is that moving objects are always shortened, okay? So you always should ask yourself, what do I expect? And what frame of reference am I in? Am I in the Muon frames of reference, or am I in the lab frame of reference? And you should answer your question before you get the calculation out so you can double check yourself. Do you expect it to be shortened, or do you expect it to be longer, all those types of things. So length contraction is consistent with time dilation, which we just saw. So just some general tips before I finish up. So it's easy to confuse reference frames. Each frame of reference sees one moving relative to the other. You should always ask yourself which frame of reference you're interested in. And imagine you're there sitting with that person or that object, okay? If it's a spacecraft, if it's a person, if it's Alice or Bob, put yourself in that head that you're stationary next to them. And you have to ask yourself what's moving relative to you, okay? You have to kind of drop in your head that the trains always move relative to platforms. It's not always the case, it depends on who you are. Now, other common errors, just using the wrong numbers in the equation. As I said, T naught and TV, L naught, LV, you flip between the two, but the first one should answer. And so what I want you to do to take away from this to help with your general intuition here is these rules of thumbs. That moving clocks run slow, moving objects are shortened, and the last one, which I didn't have enough time to discuss, is that moving objects are more massive. That essentially means that as something goes closer to the speed of light, it actually appears heavier and heavier and heavier. So just some other implications, just quickly. Oh, was that a question?
Yes.
Yeah?
With the mass increase, what actually at like the atomic level is actually making you more heavy?
That's a really good question, and again you have to remember, one, it's relative to something else. So for example, if I was just in a spacecraft, right, I wouldn't be observed to be getting heavier to myself. I would still weigh whatever I weigh right now, right? But to someone else it would appear as though I'm getting heavier. But the trick here, and this is where the HSC syllabus kind of fails, is that it's not really mass that's changing, it's actually momentum. So your momentum appears to change. Now, if you want to trace it back all the way to the microscopic level, this is where you've got to start playing games with the convolution of general relativity and quantum mechanics, which breaks down. But at the end of the day, the way to think about it is that you've got energy locked up in the mass of an object. E equals mc squared, and you've actually got an extra term there that involves momentum. And so the atomic level doesn't change at all. Okay, what ends up changing is your perception of the energy involved there and how much they have. It's kind of strange to think about. But if you want to know anything more about that, and it's beyond the HSC syllabus, just Google full form of E equals mc squared. What you'll find is actually it's E equals mc squared plus p squared c to the 4. And so really, mass isn't changing, it's actually momentum. And that's all got to do with your velocity, which you can understand, rather than actually your physical mass gaining. But it's the way the HSC syllabus expresses it, because it's kind of easier to conceptualize, unless you imagine the atomic scale. Good question. Alright guys, I'll just finish on this slide, and I'll open up further questions. I just want to, showing again this mass increase with speed. You can actually use it, quite interesting, to show why you can't exceed the speed of light just with this equation, right? Because if you've got 1 minus v squared on c squared, as v goes towards c squared, you've got 1 minus 1 on the denominator. So as you closely approach the speed of light, it appears that you need your momentum becomes gigantic. That means you essentially need infinite energy to get you over the barrier that is the speed of light. The other one is the implications that I mentioned, E equals mc squared. But sometimes I get these questions, they're like, well, okay, so what's so important about special relativity, right? You have to learn it during the HSC, but does it play any role in everyday life? And it does. It's very important to the way, for example, GPS work. If you don't, GPS work all on timing. If you don't take into account the speed of the satellite as it changes, you actually won't get the correct triangulation of your position. The other one, obviously, is particle accelerators. If you didn't know about the speed of light and how your time and length change, you wouldn't be able to build those. And for me, who is a radio astronomer, you find often around black holes, things are traveling at relativistic speeds close to the speed of light. And without special relativity, I'd never be able to analyze these types of influences and talk about how galaxies change and evolve. So, guys, I just want to finish. I'll just finish again on the quote of Feynman. So just remember that you just have to brace yourself. It's not difficult to understand. It's just absolutely ridiculous, okay? So if you're finding it bizarre, you're probably on the right track, okay? So thank you very much, guys. Hope you enjoyed and learned a couple of things, and open to any questions.
Okay, thanks a lot, Joe. Does anyone have any questions they'd like to ask?
Yeah, I've got another question.
Sure.
Okay. So if I have an object that's like going 99.9999% the speed of light, and I approach into a gravitational field, will that gravitational field accelerate me faster than the speed of light? Because gravity, doesn't matter what mass you are, you can accelerate still.
Yeah, okay, so there's a couple of things here. No longer special relativity applies. Special relativity is broken down because you're going close to a gravitational body. This is what's so special about general relativity. General relativity showed that gravitational bodies can be modeled as frames of references that are accelerating. And so more or less what you find if you put it into the general relativity framework is that you can't be accelerated above c. So what happens is you just keep going closer and closer and closer, and you're just using more and more energy to get that extra 0.999999, but you'll never exceed the speed of light. So you'll never bump over.
Thanks.
Any other questions?
No, we're all good, thanks.
Okay, well if there are no more questions,
Alright.
oh, is there one from Fort Street High School? No?
Oh, I think.
Yes, Fort Street?
Right. Is there some way in which calculating a special relativity result is changed once you have to receive the result? As in when it comes back, it's got some sort of, the actual travel back causes some sort of special relativity incident to occur so as that it sort of normalizes itself out. I was thinking of the twin paradox in which they both have to be older than each other.
Yeah. So so you're just discussing it. Yeah. So the twin paradox is a fun little thought experiment. The idea here, guys, for anyone that might not be familiar, is that you got two twins. I put one of my twins in a rocket and I travel him out to Alpha Centauri at the speed of light, and I get him to turn around and come back home. Now, as I said, remember, you should always ask yourself, whose clock's moving slower? So if I had a telescope and I looked in this spacecraft and I looked into my twin's wristwatch, I would find his clock's moving slower, right? But if he did the same thing, because Earth's moving relative to him, right, and he got his telescope out and looked at my wristwatch on Earth, he would find that my clock's moving slow, because remember, Earth is moving relative to him too. So, which one's right? Obviously, someone has to be right in this situation. So, the answer is, when he goes around Alpha Centauri and comes back, and we both go to compare our wristwatches, obviously someone has to be older, right? You can't both have that situation. The answer is, actually, I will be older, and he won't. And what's happened here, and what's changed, is, you remember, he had to turn around, right? And so what happened is, he had to go through a de-acceleration and re-acceleration. So he actually changed inertial frames of reference. The way I like to think about it, guys, is imagine, on my birthday, every year, I sent a message to him over a radio wave saying, happy birthday, mate, have a great day, right? As he's traveling to Alpha Centauri, those messages only travel at the speed of light, right? And so what happens is he'd only get maybe, say, 5 of those, all right? But even though I've lived 10 years on Earth. But I've sent them once every year, as far as I'm concerned, every year. Now imagine he turns around, what happens is, on his way back, he will collect the rest of those. So he will collect, say, the extra 6 or 7 that I've sent. He will have more on the journey back than he will have the journey away from me, okay? And so the trick there is that the frames of references have changed when he did that U-turn, okay? And that's why you break it down, and that's why essentially you're able to resolve that paradox. So it's actually technically not a paradox anymore. But it was one of those first things, or which one's right? Because everyone sees a different clock moving slower. Did that kind of answer your question?
So the aging occurs in the lateral movement. It doesn't occur when he's going towards you or away from you. It occurs in that distance between, because that's where you find.
The aging occurs at all points. It appears it won't occur until he's done that U-turn. Yeah.
Okay. Cheers.
Okay, I think we've got time for one more question if anybody has anything they want to ask. No? I think we're all done. Well, thank you so much, Joe. Can you join me in thanking Joe for his presentation today? And thanks again for joining us, everyone. If you're interested, teachers, we have a presentation coming up on the 10th of November, which is particularly for Year 10 students. Our presenter is Professor Tamara Davis, and she'll be talking about the Big Bang Theory and the formation of the universe. Again, thanks a lot. We'll see you next time.
Thanks, guys.